think nuclear engineer, what pops into your head? Is it Homer Simpson? Or maybe someone in a full-blown hazmat suit, surrounded by glowing green stuff? Well, the reality is not only way more interesting, it's actually on the brink of a massive AI revolution. Let's get into it.
All right, so first up, we've got to bust some myths. We need to get way past that pop culture image of what this job is all about.
I mean, that's the real question, isn't it? Forget the movies and TV shows for a second. What does the day-to-day actually look like for the people who are responsible for harnessing the power of the atom?
And you know what? This is a great question. This Reddit user nails that perfect mix of genuine technical interest and, just practical curiosity. So yeah, let's tackle that famous hazmat suit question head on. And boom, there's our answer, straight from someone who's actually in the industry. The whole hazmat suit thing, it's pretty much a myth for engineers. The real work happens far away from any danger zone. So if they're not doing that, what are they doing? So what does a day in the life really involve? Well, it's a world of high-stakes computer modeling, super complex analysis, and critical planning. And yeah, most of it is done from behind a desk.
You see, this is what's so fascinating. This isn't just about maintenance or flipping switches. These engineers are the strategic brains behind the entire reactor. They are literally planning every single move, predicting every possible outcome, and running disaster scenarios for things they hope will never, ever happen.
And here's another engineer breaking it down even further. Just think about that for a second. Designing the exact sequence to refuel a nuclear reactor. It's like playing a game of 3D chess where the stakes are unbelievably high. You have to make sure that core behaves exactly as planned. And, of course, you've got the, let's say, less glamorous side of things. I love this quote because it's a hilarious reminder that even in a field as ridiculously advanced as nuclear engineering, a huge chunk of the job is still about communication, collaboration, and, meetings. So, as you can see, it's this incredibly diverse, super analytical job. From designing the core itself to assessing risk, it all comes down to guaranteeing safety through just meticulous, careful planning. But here's the catch. All of that planning depends on one crucial thing: data. And getting that data, well, that presents a massive fundamental challenge. You see, every complex system has a weakness, a blind spot. And for nuclear reactors, the big one is the simple problem of knowing what's happening everywhere inside the system all at the same time. I mean, just think about it for a second. The inside of a reactor's cooling system is an unbelievably hostile environment. We're talking intense heat, crushing pressure, and of course, radiation. You can't just slap a sensor on every single inch of pipe to see what's going on. It is physically impossible. So this is the gap that engineers have been trying to solve for decades. On one hand, you have traditional inspections. They're slow, they're expensive, and they only happen when you shut the whole plant down. They give you a snapshot. But the ideal, the holy grail, that's a live, continuous, totally comprehensive view of the entire system's health in real time. So how do you see the unseeable? Well, you build a perfect virtual copy of it. And this is where we step into the next generation of engineering, the digital twin. Now, a digital twin isn't just some fancy 3D model. No, it's a living, breathing simulation that is perfectly synced up with the real thing. It takes the data from the few sensors that do exist to accurately simulate what's happening in all the places that don't have them. And this is the kind of system we're talking about, an AP1000 pressurized water reactor. Just look at how complex that is. The whole point of a digital twin is to give engineers a live, almost X-ray view into every single pipe, valve, and joint you see there. But to make that virtual copy truly live, to make it update in real time, you need something incredibly fast and incredibly smart. You need a whole new kind of AI. And this is the breakthrough. Researchers have developed an AI model called a Deep Operator Network, or Deep ONET for short. The best way to think about it is that it creates thousands of virtual sensors that can predict what's happening in places where a physical sensor could never survive. So how does it work? It's actually pretty elegant. Think of it like this. You have two parts. The branch network sees what's happening now by looking at the data from the real physical sensors. The trunk network knows the map. It understands the physical layout of all the pipes. The AI combines what's happening right now with the map to predict the conditions everywhere else in between. It's brilliant. Okay, so the theory is amazing, but does this thing actually work? The results are,
Well, they're frankly pretty stunning. 1,481 times. That is the number you need to remember from this research. That's how much faster this deep-on-it AI is compared to our best traditional computer simulations. A calculation that used to take minutes or even hours now happens pretty much instantly. And that speed is the key that unlocks true real-time monitoring. And here's the proof in the pudding. On the left, you've got the ground truth, what a super slow traditional simulation says is happening. On the right, the AI's instant prediction. Look how perfectly it predicts the coolant velocity. It's almost a perfect match. And it gets even better. Here, the AI is predicting turbulence. That chaotic churning flow you see, that's a huge cause of wear and tear on the pipes. Being able to spot that forming in real time is an absolute game changer for safety and maintenance. And finally, let's look at pressure. Notice those red hotspots forming around the bend in the pipe? The AI nails their location and their intensity. Being able to pinpoint these high-stress areas lets engineers prevent tiny problems from ever becoming big ones. So, what does this all really mean? It means the entire job is about to change. Instead of just reacting to problems found during an inspection, the nuclear engineer becomes a truly proactive manager. They're armed with a live, predictive crystal ball that shows them the health of the entire system. They can literally see into the future of the reactor. And honestly, this leap forward is so much bigger than just nuclear power. This is about making any complex, harsh, or totally inaccessible system completely transparent. Think about jet engines, chemical plants, maybe even the human circulatory system. If we can see inside a reactor, what impossible places will we be able to see, predict, and perfect tomorrow?